Hello students, welcome to the class once again. I hope you are all doing good and you are in the best of your health. And you are practicing problems in physics that already we have done. We have done a lot of chapters till today. We would have practiced problems on kinematics and laws of motion. Last class we were discussing about Newton's second law and we discussed problems based on Newton's second law. We saw how tension were applied along the pull-less two sides, T and 2T. On the two sides, we saw how the acceleration on the blocks can be related. Acceleration of the blocks can be related. We saw how to apply the pseudo force. In today's class, we are going to understand Newton's third law of motion. I know you are already knowing about Newton's third law of motion, but today we'll see how differently we are going to use it in certain cases. How sometimes we have to apply forces using the concept of Newton's third law. How sometimes we have to be so much cautious that let us not frame a wrong equation using the concept of Newton's third law. So first of all, let us understand the statement of Newton's third law. It says that to every action there is equal and opposite reaction. So let me write down this statement which most of you are all knowing also. Third law, the statement is to every action there is an equal and opposite reaction. To every action there is an equal and opposite reaction. There is an equal and opposite reaction. Now what do we mean by this? And first of all, let me tell you, action and reaction, these two forces acts on two different objects. Remember this point also, action and reaction acts on two different objects, not on the same object. So action and reaction acts on two different objects. Now, a very basic example. To every action there is an equal and opposite reaction. Suppose if I actually push this duster, what I'm going to do, I'm exerting a force on this duster. Don't try to punch the wall of your house. Don't try to do that. That would be actually very painful. And you know why that pain comes to your hand, why your muscle pains, why your hand pains. You know why? Because as you're going to exert force this object thinks that why is someone hitting me? I'll also hit the person with the same force. This will exert the force of same magnitude on my hand. So if you actually punch the wall, you are going to feel pain because the wall is punching you back with the same force, and that's why you feel pain. So this is the concept of Newton's third law. If you apply a force on some object, that object will apply in return the same force to you, to the source actually which originally applied the force. But let me tell you, Newton's third law is so much useful that we can see its day-to-day application. Suppose a rower rows a boat. What he does, he actually uses the bar and actually rows he actually uses the rower and actually pushes the water backward. In return, water applies a force of same magnitude on the boat in the forward direction, and hence the boat is moving forward. So I told you this action and reactionary forces acts on two different objects. So action force that the rower is applying on the water, that is applied on the water. And reaction force that the water is applying on the boat, that is the reactionary force which is acting on the boat. So we have to take very caution. These are acting on two different objects. So so first of all, we need to be very cautious, understand and decide the system. If you take the water as system, so water will be experiencing a force in the backward direction. If you take boat as the system, so boat will be experiencing the force in the forward direction. Two different systems we have taken, and if we combine boat and water as system, net force will be 0 because one force on water will be in towards backward direction and one force on boat that will towards the forward direction, and both will cancel out each other's effect. This was all about rowing a boat. Many examples you can think of. In the first class, while studying Newton's law, I also told you such examples. If you hit a ball, suppose you are playing cricket, the baller is balling to you and the ball reaches to you, you hit the ball with your bat. Now ball also in return will apply a force on the bat, so your bat slightly it deflects in the backward direction. Suppose you are directing the ball in some other direction, the ball will also exert the force on the bat in the just opposite direction. And suppose if you play football, you are kicking a football will also in return will exert the same force on you. But you see, we do not feel that force, we do not feel the acceleration on us in the backward direction because our mass is quite more. The ball mass is quite less. Now, if the ball mass is quite less, its acceleration will be very more. because applying that same the amount of force. And now if that amount of force acts on your body, your acceleration will be quite negligible or nothing, because your mass is quite more. So you're not actually feeling that effect of that force. Next thing, suppose the ball is very heavy. Let us say if you go to a gym, you'll find that such heavy balls are there. Let's say you take a 15 kg ball, keep it on ground. Its shape is like a football. Now if you try kicking that football, you can feel the pain, because again the force will be of so much magnitude that you are going to feel the pain in the backward direction on your muscles. Now let us discuss a very important case, a very simple case. This is the horse and cart case. This is given in a very standard book, and the case is very much interesting to know. Now what happens generally if you take a horse and cart case, or if you can take, if you have, most of you must have seen this call in Hindi in many places, in towns and in rural places. We see there's a tanga, we will be finding that in many places. What happens, this horse is trying to pull the cart in the forward direction. Now just now I told you Newton's third law. I told you that if you are applying a force on an object, the object will apply the force on you in the backward direction. So let's say horse is applying a force on the cart with the help of this rod that we can see. Let us say the force which it is applying on the cart is force F1. Now in return, the cart will also apply a force on the horse, and horse will be experiencing a force F1 in the backward direction. So if we take overall the horse and cart system, we'll be finding that net force on these two will be 0. Due to the effect of the force that has been provided by the horse on the cart and cart on the horse, we'll be seeing that net force on 0. So why does the horse and cart accelerate? So being force 0, being net force to be 0, why horse and cart accelerate? This is the first question that comes. Why horse and cart accelerates? Now to answer this, let us think once again what mistake we are doing and how we have taken the system. Now we took both as a system, and we are making somewhere, we are doubting ourselves, somewhere we are making mistakes, so that's why we are not getting the required result. So what I'm going to do, I'm going to change the system. This time let's take horse as the system. So if we take horse as a system, see what forces are acting on it. We can see on the horse, the force is applied by the cart in the backward direction. So if we mark here the horse, this is our horse, and let's say its mass is m1. So a force of magnitude F1 is acting in the backward direction. As you can see on the horse, the force is acting in the backward direction. Next, why is it accelerating? We are having the force in the backward direction, but still the horse and cart both move in the forward direction. So where is the mistake we are doing? And if only this force is acting, the acceleration of the horse will come out to be force upon its mass. So you will get a backward acceleration. So horse will move backward. And now we can see force F1 is acting on the cart in the forward direction, so cart will move forward. So horse moves backward, cart moves forward. Both are going to collide, and horse is going to land on the cart. Why the system moves in the forward direction? Again, we are making some mistake. Think of the shoe of the horse. Think of this horseshoe. Horse is applying a force on the ground in this direction, which I am going to show you in this direction. Let us call this as force F2. So horse is applying a force on the ground because he is going to press the ground in this direction. In return, ground will apply a force on the horse in the just opposite direction. So what I'm going to do, I'm going to mark this opposite direction force as acting on the horse as F2 this. Now this F2 will have a forward component. F2 will have a forward component. So let me write its forward component with a new force as small f. This is the forward component of force F2, that is F I have marked. Now the system is quite clear. We have taken horse as the system. We have written all the forces. Now we can find the acceleration of horse. Since it is moving in the forward direction, let us take its acceleration as A of horse. So A of horse will come out to be net force F minus F1 divided by mass of horse, that is we have taken as m1. We have taken mass of horse as m1, so we have taken this. This comes out to be acceleration of horse. Suppose once again, I am going to recall you, let us say cart is also moving. If cart is also moving, and if the acceleration of cart is somewhat different than a1, somewhere either the cart will move backward or it will come forward, and then both are going to collide once again. Either they are going to get separated from each other or they are going to collide. So to move consistently together, both acceleration have to be same. It has to be same. Now let's draw the FBD of the cart. So free body diagram of cart, let us take the mass of cart as m2. What are the forces acting on it? So forces acting, one force is by the horse and that will be F1 magnitude. Come to the diagram. One force is acting on the cart of F1 magnitude. So we can say acceleration of cart is F1 by its mass, and its mass we have taken as m2. But still we are not done. Still we are not done. You can see that these are the wheels we are touching the ground. Wheel will exert a force on the ground. Let us say wheel is exerting a force on the ground, and let's say this force is F3. In return, ground will exert a force on the wheel in this direction. So we are having F3 force. So let's come here. I wish you all can see here this force F3 here, which the ground is exerting. So F3 will have a forward component. Let's call its forward component as F dash. So now now we have decided all the forces. This F dash is actually a component of F3 acting in the forward direction. So we can write net force or acceleration this time as F1 plus F dash divided by its mass m2. This is the acceleration of cart. So acceleration of cart comes out to be F1 plus F dash upon its mass as m2. Now both have to move consistently together with same acceleration. You can see that F3 and F2 can change. F3 and F2 can change. So they will try to keep its value in such a way that acceleration of horse and acceleration of cart is same. So therefore acceleration of horse is equal to acceleration of cart, so that both can move together. So we'll be having F minus F1 divided by mass of horse, that is m1, is equal to F1 plus F dash divided by mass of cart, that is m2. So we got this relation. So what thing that we need to take care of? First of all, you have to take very much caution while applying the forces. You have to be very much aware about which system you are talking about, which system you are taking into consideration. So first of all, deciding the system is very much important. If you combine objects and then you decide the system, do not take internal forces into consideration, take only the external forces. Second, if you take only one object as a system, then you have to see what other objects are applying forces on the object that has been taken as a system, and then you apply the forces, then you relate the forces, and then you find the acceleration of the object. This is how we are going to decide the system, then we are going to apply. And now we have also used Newton's third law. To every reaction there is an equal and opposite reaction. If one object in contact with other object, or not in contact with, if they both are attached with the help of a string, if one object exerts a force F on other, the other will also exert the force F on the first object. This is the statement of Newton's third law. This is how we are going to apply Newton's third law in this case. Now comes the point. Let's see some more examples where we can use the concept of Newton's third law. This case was clear to everyone, I believe so. Horse and cart problem, why the cart accelerates and why the horse and cart move together. Hope that now it is clear to everyone. It is due to the forces that is applied by the ground that we need to also consider in the case of horse and cart. Now let's see some more examples. Very simple example is walking. You know, why do we walk? Why it is so much easy for us to walk on a rough surface and it is difficult for us to walk on a slippery surface or a very smooth surface. It will be very difficult for us. Friction certainly plays a role, but still I'm not using the concept of friction here in today's class. When we talk about friction in the next class, then I will tell you how friction actually acts and operates. Walking. See here, suppose a boy is walking with his feet in this way. You can see, let us just imagine, I'm not good at drawing, but I know that you all can forgive me for my drawing, which most of you are tolerating also. Every time I draw something different, you know, see this boy is actually targeting itself, targeting it to move forward. This boy is trying to move forward. Things, I know most of you must be smiling now, what kind of diagram has been drawn here. It's okay. Till the time we understand physics with all this diagram, it is okay for us. Now if he's trying to walk, if you try to walk, what you do, you actually press your feet, in this way. You do not keep your feet straight, you press your feet in the backward direction. In slightly, your front toes that actually goes and pushes the ground in this direction, that is making an angle with the horizontal. You do not walk keeping your feet straight. Then again you have to force the ground in this direction. You apply a force in this direction as shown. Now what happens, we all know, just now we have learned the concept of Newton's third law. Ground in return will apply a force on your feet in the opposite direction. So this is the direction of force which ground actually applies on you. Now we can see that this force will be having two components. There will be two components of this force. One, the forward component. One component shown in this direction, let us use that as small f, and one will be having in the vertically upward direction, that will be shown as f dash. Let's say it will be having two component. Let me mark this as quite more so that you may have a better understanding. F is having two components as shown here. Now see, this force, which is actually the forward component of the force that ground was applying, this force is responsible for walking. This force is responsible for you all to walk, responsible for walking. The force applied by ground and its component taken along the horizontal direction, that force is responsible for taking you to the forward direction. Now, what this force is doing? This force is actually balancing your weight. Because you're touching the ground, the ground will actually exert a force on you, and there will be a weight, and your weight will be balanced by this force. This is actually balances your weight, balances weight. So this is the this is actually use of this force f dash. F is responsible. Now we understand again by using the concept of Newton's third law, we got that this, if Newton's third law was not applicable, it would be difficult for us to walk. We are only walking because of usage of Newton's third law. To every action there is equal and opposite reaction. Three examples we saw: rowing a boat, hitting a ball with a cricket bat, kicking a football, and even this year walking also. There are many more examples which you can think of. Let us take one more example. Let me talk of some more examples. Let us say we have a very heavy block here. We have a very heavy block. Let's say its mass is capital M, and on it we have kept another block whose mass is small m. Now what you are doing, you are standing back, and you are trying to push this heavy block. You are trying to push this heavy block by standing on the ground. You are trying to push this system in the forward direction. Now, which force is responsible to move this one? You are applying a force on this one. You are applying a force on this, but actually both the objects are moving together in the forward direction. Both move together. This is generally, every time we will observe, you take a big box and on it you keep some load, you are going to push the bigger box, you will find that the load that is kept on the the lower one, which is also moving together, both being stick to each other. So which force is responsible to move this? Actually, that force is actually the contact force, or let's say that is the friction acting between these two surfaces. We will talk about this friction in detail in the next lesson, don't worry about it. So hence this is moving together. Now, as this is applied, what happens? A force has to act on this. This force will be in the forward direction. I am taking this as small f. Now again from Newton's third law, a force has to act on this block in the backward direction. So I am marking a force small f acting on this block in the backward direction. From Newton's third law, if a force F is acting in the forward direction, so a force F of same magnitude should act on this bigger block. So we got one more application. I want you all to note down till this example, then I will continue from here.